Let us discuss about rotational motion of a body and various terms connected with the rotational motion. To understand rotational motion, let us assume a body of any shape and size like this, and we assume that it moves around a line, it moves around line such that this way, and this line is sometimes known as axis of rotation. Axis of rotation. So the condition is that all the particles, all the constituent particles of this body, let us assume various large number of constituent particles are there, and all these particles move in concentric circles around this axis of rotation, which can be shown like we have this body and this axis of rotation, let us assume it is here. Then all the particles, for example this particle will move in a circle here, this particle will also move in a circle here, and similarly nearer particle also moves in circle. So all the particles of this body, they will move in concentric circles such that the centers of these circles lie on this axis of rotation from here. So such motion is known as rotational motion. Rotational motion. We'll write like this. Such motion is rotational motion, and the point, this is called center of rotation, and the line around which it is moving, that is called axis of rotation. Since all the points are moving, they describe certain angle. Now all particles of the body are moving along the circular uh, or concentric circles, and that means all particles are moving around the axis of rotation. So in certain time of period, let us assume the particles, or let us say a particular particle around this axis of rotation here, a particular particle was at point A, and after some time it is on its motion along the axis, it reaches at point B from A to B, such that it describes a angle. It describes an angle from here to here. Let us say this angle is delta theta. Then this delta theta is called angular displacement. It is called angular displacement and measured in radian. If this body covers this delta theta time, that delta theta displacement in small delta time, delta t, then the ratio of delta theta and delta t, ratio of delta theta to the time delta t, that is delta theta delta t, then this ratio is called average angular velocity, and it is measured in radian per second. It is measured in radian per second, and this is called average. But if the movement of this particle from here to here is observed in very small time, that is when this delta t is very small, then such that we can write in this form that if limit of delta t time approaches to 0, then this expression of delta theta over delta t, it is written as d theta over dt, and it is represented by omega, and this omega is called instantaneous velocity, angular velocity. Instantaneous angular velocity, and it is measured in radian per second as such, but only difference is that this time may be uh, any value, but this time is very small, and when time approaches to 0, then this quantity becomes instantaneous velocity. That means that is angular velocity measured at a particular instant of time. Now, if velocity is not constant, if it is not constant, then it will be varying velocity, angular velocity. And if it is so, let us assume that at time t1, this angular velocity is omega 1, and at some time later than this, that means at time t2, this angular velocity is omega 2, then ratio of change in this angular velocity, that means like omega 2 minus omega 1, and ratio of this to the change in time, that is t2 over t1. This happens when velocity, that angular velocity is not constant, that means it is changing. So initially velocity we can measure omega 1, then after small time or at time omega t2, its angular velocity will change to omega 2, then the difference will be, we can write delta omega, and difference in time we measure delta t, then this quantity is called average angular acceleration. And measured in, this was measured in radian per second square. And as we have studied here, as we learned here, if this time again becomes very small, if the time of observation of this change in angular velocity is very small, that means if limit of this delta t approaches to 0, then this quantity delta omega divided by delta t, it is written as d omega over dt, and it is denoted by alpha, and this is called instantaneous acceleration, rather angular acceleration. Angular acceleration, and it is measured in radian per second, and which may be stated at time rate of change of angular velocity is called angular acceleration. So let us define one more important term connected to the rotational motion that is called angular momentum. Angular momentum. For that, let us assume a body. We assume a body constituted by a large number of particles, and it is rotating about some axis of rotation like this. We assume this way, and let us assume a particle of this body, constituent particle, one of the constituent particles, it is here, and its mass is m, let us assume, and it is moving towards in this direction and lying at a distance from here, at distance, or let us say r. And if it is moving with the linear velocity v like this, and it has mass m, then naturally it will be having a momentum p. Then a quantity defined as the product of this perpendicular distance and this momentum, linear momentum, it is called angular momentum. That means it is denoted by L, and it is written as r. This r, which is a perpendicular distance of the particle from the axis of rotation, multiply by its linear momentum p, and this is called angular momentum. It is a vector quantity, and according to vector algebra, this angular momentum will be perpendicular to r as well as p. It means in this diagram, r and p already they are perpendicular because this angle is 90 degree, and then L will be along this axis of rotation upward. L will be shown along the axis of rotation, and which is perpendicular to r as well as p, and it is measured in kilogram meter per second, kilogram meter square per second. It is meter square per second, because we have velocity, this mass and velocity. So mass comes kilogram, 1 r here, 1 r comes from velocity, so kilogram meter square per second, that is the unit of angular momentum. And since it is a vector quantity, it can be represented in terms of components such that L can be written as I cap Lx, that is x component of this angular momentum, plus j cap Ly plus k cap Lz. So these are the three components, and the value of these three components can be determined by solving the product of these r and p, and which can, these two terms can also be written in their component form, which we can write r as I cap x plus j cap y plus k cap z, because we know that this is a these are the components of this r in x y z direction. Multiply by, we can write components of p along x y z directions like I cap px plus j cap py plus k cap pz. Now we know that the vector product of two vectors can be obtained by writing determinant using uh, these components as the elements of the determinant, like we can write I, j and k, and then first line we'll write as x, y and z, and then the components of momentum, that is px, py and pz. And writing these, we can open determinant, like let us expand along with I, we get ypx minus ypz, sorry, ypz, I multiply this with this and then z with zpy plus j cap is equal to, we multiply z with px, z px minus xpz plus k component will be written as xpy minus ypx, xpy minus ypx. So these are the components. Now these are the components of momentum, which you can write here also: I cap lx plus j cap ly plus k cap lz. Now let us compare the coefficients of I, j and k both sides. On comparison, we get that Lx will be equal to, from here, because coefficient of I is this, so we can write y p z minus z p y, and then I have to find Ly, that is coefficient of j. Here coefficient of j is this, therefore we will write Ly is equal to zpx minus xpz, and finally coefficient of k, that is we have Lz is equal to, from here we have xpy minus ypx. So we get three components, values of the components of angular momentum along Lx, x direction, y direction and z direction. But if the motion of the object, as we have seen here, the motion of this object or particle is in xy plane like this, such that the axis of rotation is along z-axis, then we can see what happens to the equation of the magnitude of angular momentum. We get, in that case, if the motion is if you can say motion is in xy plane, then z component will be 0 and pz will also be 0. In such case, if we see in this equation, then z and pz will be 0, so this term will be 0. Here this pz and this z will be 0, so this term will be 0. In this case we don't have any z and pz, therefore we get, on comparison, Lx comes out to be 0, Ly comes out to be 0, because Lx is composed of pz and z, which is 0. Here also z and pz, it makes the Ly 0, and we get Lz, and Lz comes out to be xpy minus ypx. It shows that if the motion is in xy plane, then the component of angular momentum will be only along z-axis. And similarly, you can find components of angular momentum if the motion is in yz plane or xz plane. In that case, we will get only Lx or Ly respectively. So after angular momentum, another important term related to angular or rotational motion is called torque. And torque is defined as the product of perpendicular distance of a particle from the axis of rotation with the force acting on that particle by which it comes into the rotational motion. That means if you have axis of rotation here, And suppose we have some particle here such that it has perpendicular distance from here, that you can say r, and if some force is acting on it, you can say some force is acting like this on this particle f, then the perpendicular component of this force, which is responsible for the rotation of the particle, rotation in this particle will rotate around the axis of rotation, and that will be only responsible due to this force F. And if we assume that if the direction of this P, this distance, and this F is theta, let us say this direction of R is this, you can say R direction, and force is here, if this is theta angle, then this is base, so the component of force along this base will be written as F cos of theta, and this component is written as F sine of theta, and this force component is the responsible to rotate this particle around the axis of rotation this way. Therefore, we define this torque tau, which is the notation of torque, as R cross this force F sine theta, and since we know that if A cross B is there, then we can write A B sine of theta. It means since angle is sine theta, trigonometrical ratio, then we can write it as R cross F. So means torque is nothing but it is cross product of the force and perpendicular distance, and here tau will also be perpendicular to R as well as F, and therefore tau will be along this line and denoted by tau. Here tau can also be expanded in the component form, and these component forms can be written as I cap tau x plus j cap tau y plus k cap tau z, and you can again write these two components in determinant form like I, j and k are components of R x, y and z, components of force F x, F y, F z along the three directions. And on expanding, we can again write, opening this determinant, we can write tau x component will be equal to y fz minus z fy, and tau y can be written as z fx minus x f z, and finally tau z can be written as tau z will be written as x fy minus y fx. These are the components of the torque, this torque along x, y and z components, and this torque is denoted by this tau, and unit is simply Newton and meter. So its unit is Newton meter. So these are the important terms which are connecting this rotational motion and its various kinds of study, and we will discuss few more things related to rotational motion in next video. Thank Thank you for watching.